probability. Uniform, continuous distribution. So now we're looking at some special formulas for it. So these are results from calculations. And so if you know you have a uniform continuous distribution, remember, uniform continuous means that when you are between A and B, it's on, and then when you are outside of A and B, it's off. And it's the height is adjusted so that that area there is 1. But having a distribution with this property, when we want to go compute the expected value, remember that is observation times chance of seeing it, and then you add up all possible values. Well, it's only the only values you have to worry about are between A and B, and when you go through this, you end up discovering that you can compute the expected value or mean by taking the average of the beginning and end point where it shuts on. Might have expected that, but if you go through the steps in this, you'll end up with this result. And so A and B are parameters that define your distribution there. With variance, so this is, remember, so you take each observation, subtract from the expected value. So you're taking the distance from the mean, you square it, so you have square distance from the mean, times chance of seeing it, and then you sum up all possible values. Because this is continuous, we have an integral, so if you go through this calculation, you'll see that you have b minus a quantity squared over 12. This is quite a bit of work to actually show that, so having this result here is pretty handy. And similarly, if you want the standard deviation, which remember is simply just the square root of variance, in this case, because we have this formula for variance, it's simply the square root of b minus a quantity squared over 12. So if you have a uniform continuous distribution, so you have to have that, so it has to have this general property and shape, then you can use these results for expected value or mean, for variance, and for standard deviation. And these formulas are useful. They do save time. So